All right. Well, thanks everyone for joining us right after lunch. Appreciate everybody coming out to hear about waste heat recovery and thermal storage for buildings and networks. My name is Sue Dougherty, and I am a program manager at NYSERDA. I manage our large-scale thermal program, and I'll be starting off just with a quick description of the funding opportunity that we currently have available to support large-scale thermal projects. And the panelists that are joining me will talk about some projects that would be eligible for the large-scale thermal program. And then a colleague of mine from NYSERDA, Lauren, will talk about a funding opportunity we also have at NYSERDA for heat recovery projects. Greg Koumoullos from Edison will talk about some of the utility thermal energy network projects that include waste heat, so he'll show some example projects. Aaron Miller from SHARC Energy is going to talk about their wastewater energy transfer technology and give some project examples there. And then Chris Devins from Trane is going to round us out and also talk about some examples of how heat recovery and thermal energy storage solutions can be implemented. So as I mentioned, I'll go through our large-scale thermal program. I also talked about this a bit at the 4 o'clock session yesterday afternoon. So if you joined that, thank you for joining again. I'll be repeating some of that information. So just some background on what large-scale thermal is in the context of the types of projects we're seeking to support through the program. Large-scale thermal is a system that provides heating, cooling, and hot water using heat pumps and low-carbon thermal resources. We're not overly prescriptive with our definition of large-scale thermal. We're really looking to solution providers and project sites to come to us with technically and economically feasible solutions. This slide just shows some examples of resources that would be considered low-carbon thermal resources. These are all complementary and can work together to produce a large-scale thermal system. Geothermal is obviously a great example of a low-carbon thermal resource, but we're also looking to support projects that recover heat. So rather than it becoming waste heat, it's recovered and recirculated through the system. Likewise with wastewater heat recovery, and then thermal storage is another opportunity that we would like to see project sites take more advantage of for many reasons, like load shifting, peak shaving, the benefits they can offer to the grid, and the ability to reduce the build out of infrastructure, delay the build out of future infrastructure by including thermal storage in a project. So a little bit of background on the minimum thresholds for eligibility for the program. We support both single building projects and multiple building projects. And when we say multiple building projects, we mean projects that are usually campuses like college campuses, medical campuses, multifamily residential complexes, could be a community, could be a street in a downtown, core area. And we support both networked and non-networked solutions. So how this varies a little bit from the program that preceded large-scale thermal is that we really want you to tell us what the best opportunity is for a project site or a group of buildings. So it may be networked and it may not, depending on energy density, costs, a range of other factors. But for either networked or non-networked solutions with multiple buildings, it must be at least 250,000 square feet. For single buildings, at least 100,000 square feet. And a little bit of background on the funding available through this program. I'll just start by saying we can support projects all throughout New York State, so we're not limited by project sites that pay the system's benefits charge. So we have funding available for projects that include municipal electric utilities. So we can fund projects in Long Island, and we can fund muni electric projects, as well as projects where the electric provider is an investor-owned utility where the customers are paying SBC. So we're really interested in making these projects work. We're out there trying to increase interest in the program and to try to find good project candidates. So if you have questions, you can come to me. and we'll sort through the details, and I can clarify what's eligible or not eligible through the program. The program is focused on supporting design projects, so we're looking for projects that have already gone through their feasibility assessment. They've already come up with a solution that they want to move through the detailed design phase and become shovel-ready projects. And the funding caps for the program are slightly different for existing buildings versus new construction. So for projects that are focused on existing building retrofits, projects are eligible for up to $750,000 of incentive, and for projects that are new construction, they are eligible for up to $300,000. There is a minimum 50% cost share for all projects being proposed to the program. And if a project site or a solution provider that's working with a project site hasn't gone through the feasibility phase yet, we do also have funding assistance for the feasibility phase. We have the FlexTech program, which is a cost-shared program. It's open enrollment. You can apply at any time to do a feasibility study or site energy planning, and we can work with you to include a large-scale thermal feasibility study in that site energy planning. And then, just to recap on large-scale thermal, that program is currently open right now, and somehow my colleagues did a very good job of making sure that we were highlighted in the brochure. So if you have this, you can find us right here on right on the inside of the first page. And you can also scan that QR code to get to our program website. There you'll find examples of projects we've supported in the past through our previous program, the Community Heat Pump Systems program. A lot of those projects would also meet the definition of large-scale thermal, so that'll give you a sense of the types of projects we've supported in the past, as well as the solution providers who are leading those projects. So round 3 is open right now. We have a due date of July 31st. So we're accepting proposals between now and July 31st. And like I said, we're really looking forward to working with potential projects. So reach out to me. You can get in touch with me at that district.thermal@nyserda.ny.gov, or come up after the session. I'd be glad to connect with you, and we could set up a meeting and we could just walk through the program. So, we're interested in working with you. And now I'll hand it over to Lauren, who will talk about the heat recovery program.
All right, thank you, Sue. Hello, everybody. My name is Lauren De La Fuente. I'm a project manager at NYSERDA on the Clean and Resilient Buildings team, and I lead the heat recovery program. So thank you to NY-GEO. Thank you to Sue for having me here today. It's actually my first time at NY-GEO, so I'm really learning a lot. So today I'll just share NYSERDA's approach to waste heat recovery for buildings and how it aligns with the geothermal industry. So this program has $27 million of funding to support heat recovery projects at existing buildings in New York State. So I'll provide more details on our funding and how you can apply at the end of the presentation. But please do come talk to me if you have a project that would qualify. All right, so I'll just start by asking, what is waste heat and why do we care about it? You saw on the previous slide that image of steaming cooling towers. That is an example of waste heat. And to give a sense of scale, when we look economy-wide, 68% of all U.S. energy consumed in 2023 was wasted through system inefficiencies. So 68% is a huge number, and that's why we care about waste heat. It's a large, untapped resource. And our goal is to reuse that energy within buildings whenever possible. So given the scale of waste heat, we need to apply the design principle of heat reuse. It's really a circular approach to energy use rather than linear. For example, you all know that heat reuse is fundamental to thermal energy networks. Being in heat recovery mode all the time is one of their benefits. And then looking at individual buildings all around us, we see that buildings throw out a lot of energy through ventilation, cooling, wastewater going down the drains. So the idea of heat reuse is definitely not new, but it is more relevant today than ever. Policies like Local Law 97 and the growing prospect of thermal energy networks are making heat recovery a cost-effective strategy for building decarbonization. We believe that heat recovery is an essential step in phased decarbonization for many existing buildings in New York State. But when do you pursue it, and how does it fit into a larger plan for the building? This is one of our guiding frameworks that we share with building owners and engineering firms. It's called resource-efficient decarbonization, which really means doing the most with what buildings already have. This approach begins with understanding existing conditions, reducing energy load, recovering wasted heat, and moving towards partial or full electrification. This avoids oversized systems and lowers retrofit costs over time. So you can explore this framework more at retrofitplaybook.org. You can follow this QR code. Okay, so here we have some early data from NYSERDA's heat recovery program, which has been open for about a year and a half. I share this to give a sense of the measures that we're funding for different types of buildings. So we have funded 61 assessments and 34 designs across the 80 buildings that have been enrolled in our program. This graph shows the measures that have been designed for, have completed their designs, which is 16 buildings. They're color-coded by building type. So you'll see that there's heat recovery from ventilation, via an ambient loop, from condenser water, from wastewater, and also from data centers, steam condensate, and we also can help fund thermal storage when it's paired with the other heat recovery measures. So one takeaway here is that optimized ventilation is effective for all building types. One thing we found from these completed designs was that the multifamily buildings were way over-ventilated, meaning the exhaust was running too much. So there's a big opportunity for multifamily to right-size the new heat recovery ventilation. And I won't go into too much detail here because it's early data based off of 16 buildings. But as more designs are completed, we hope to publish more data about the estimated costs and savings for each of these measures for various building types. But now I'll move on to two projects that are farther along in their construction. I'm highlighting two case studies here from NYSERDA's Empire Building Challenge. The first is the Whitney Young Manor, and I believe Aaron can talk about this one more in depth also. This is an affordable multifamily complex in Yonkers that is converting from electric resistance and window AC units to a water-based distribution system. This, in the middle, is a simplified decarbonization roadmap for the two buildings, with the heat recovery measures highlighted in orange. Those measures are heat sharing between cooling and domestic hot water production, ventilation, and wastewater heat recovery. The full retrofit will cut carbon emissions 81% by 2035. The second building I'll highlight is 345 Hudson. This is a commercial building in Manhattan that's developing a low-temperature hydronic loop and using energy recovery ventilation along with other measures. These measures allow for heat sharing across spaces and the option to connect to more sources and sinks in the future. They expect a 90% emissions reduction by 2035. And the full case studies for these two buildings are available on retrofitplaybook.org, so you can see those in depth. So how does this building level heat recovery tie back into thermal energy networks? So as it stands now, New York State doesn't have thermal energy networks everywhere yet, but you all, utilities, communities, and NYSERDA are doing an incredible job in developing pilot projects. And so the question really is, should buildings wait 5 to 10 years for the network to come to them? Our answer is no. The building level heat recovery can happen now. Building level work can be done in parallel with utility and community scale networks so that the buildings are ready when the network comes to the neighborhood. Also, a benefit I'd like to highlight to the geothermal industry is that in reducing a building's peak load with heat recovery, The geothermal infrastructure can then be right-sized and more cost-effective to the owner. All right, so now to the fun part. How much money do we have to provide? So the funding here. The heat recovery program currently offers $27 million in funding across 4 categories. We want to support engineers in asking how much heat does a building expel, and can it be utilized elsewhere in the building or stored for later use? So this funding is available to all existing buildings in New York State except for single family. And as Sue mentioned, similarly for this program, we have funding to support both SBC and non-SBC sites. So if the building is on NYPA energy, then we can support those. So just starting at the top 2 green rows, we offer feasibility and design funding to actually just help develop the projects. With category 1, the assessment, we pay up to $40,000 for engineering consultants to just simply quantify the rejected heat from the current operations at the building. With category 2 project design, we offer up to $80,000 for engineers to develop a viable design for a heat recovery project at the building. Really, the idea with the feasibility and design funding is for NYSERDA to support as many projects as possible in the planning stages and then pass most of the projects off to the utilities through clean heat. The yellow row here is a category 3 heat recovery demonstration. This offers $2 million of implementation funding for select innovative heat recovery projects. And that funding is in yellow because it'll be competitively awarded to only the most impactful and scalable projects. Proposals for that category are due June 3rd. We also had a webinar that's on YouTube. You can find it that goes in depth about the requirements, how to propose, and the evaluation criteria. Lastly, the 4th category is for manufacturers of heat recovery solutions to expand their business in New York State. So we offer $100,000 to help develop their business. We also have the list of qualified heat recovery solutions on our website, which includes SHARC and Trane. All right, so just to close out here, we have funding to help you develop your heat recovery projects. We're socializing the design principle of heat reuse and resource-efficient decarbonization. So if you have any customers that are trying to take advantage of a thermal energy network, please don't wait. Come do a project with us. Apply the concept of heat reuse just to the building. And if you have any questions, please come talk to me. Thank you.
Good afternoon. My name is Greg Koumoullos. I am the department manager for the Thermal Energy Networks group here at Con Edison. If you're not familiar with Con Ed, we are the local utility for New York City and Westchester area. So we have all the electric, gas, and for Manhattan steam for much of that area. And now we are really excited about exploring this new space of thermal energy networks. So, we really were kind of birthed out of the UTENJA law that was passed. So back in July 2022, utilities like ourselves and the other utilities in the state were required to come up with some pilot projects, and we at Con Ed really leaned in pretty hard, and we're pretty excited. So we've been developing them over the last few years, and we actually are at the very end of our design, where in the next month or two, we're going to have fully 100% designed out projects that are construction ready, just waiting for approval from our regulators. So I'm going to hop in quickly here into the R3 projects and really show you kind of where they are and really how they work from a higher level now that they're kind of more close to the final design. So the first project here, and they're all slightly different. This project really is a geothermal project. This is a district geothermal project. We went into a community and to see where could be a good place to kind of put these projects. And the idea behind this project was really creating that blueprint that can go into any neighborhood and really install some of these type of projects. So this neighborhood here in the city of Mount Vernon, it's a dense residential area with some mixed use. So we have 1 to 4 family homes. We have some multifamily homes. We have several religious worship buildings. We have a medical office center, a fire station in part of the project, the recreation center. And really, we're installing a 2-pipe system here. It's going to be probably 12 to 14-inch pipe being circular in the area here. We'll be erecting an energy center building, which I'll get into soon. And we actually targeted this area for a couple of reasons. It actually started from an original study where we're looking at leak-prone pipe into our gas system. So we identified a section of leak-prone pipe I know there's a sensor here, but I'm not going to. This one? There we go. There's a section of leak-prone pipe here on this project in which it was an 1890 cast iron steel pipe, 8-inch, that is redundant. So we targeted originally as a project to see if we can just make a small network by putting a bore field here and tying these houses. So we worked with CDM Smith on that project, and then when this new thermal energy networks kind of developed into these new projects, we actually went and expanded this project to the whole neighborhood here, which we see here today. So the final count of houses is going to be about 42 buildings that will be connected to our loop, and we're super excited about it. Some of those buildings that you see here, just to give you a sample, this is the fire station. They're going to be fully converted over, and these projects are going to cover the cost for all the conversions. So it's quite a bit of house conversions. So we have the fire station, we have multiple churches, the office building, a lot of homes, and this is going to be an intense project. This is all voluntary, so all our projects in New York State, our U10s, are fully voluntary. We're not required to join them, so we have to build a lot of incentives in place to make sure we're protecting our customers that are signing up. And for almost all the projects, the utilities are picking up all the costs for the building retrofits. And finally, the one new building we're having here is one new customer is our Energy Center building here. So this is a rendering of that building. It's really a key area here because we are working with the community. We're building this building in the best part of the loop, which happens to be on near City of Mount Vernon property. And when that property was already slated to have office buildings for the emergency department to be built on that building. So we kind of partnered with them and are building the building on their property here. So the first 2 floors are really for our U10. And we're building an additional floor here that they're going to be able to use for their much-needed emergency services department in Mount Vernon. So it's a great partnership. So instead of us compensating the city for easement rights for the boreholes, we're using that offset cost to build this extra floor. So it's kind of a win-win for both us and for the city. Okay, next project I have is in Chelsea. Chelsea's in downtown Manhattan. If you've ever been downtown by the Chelsea Market, Chelsea Market's right here. And really, what this project looks at is truly a waste heat project. So this project is pretty intuitive, and we're really sharing and transferring heat between. It's a heating and cooling project. We have our kind of main customers here. This is our main resource here. So this is 85 10th Avenue. It's a large commercial office building which houses several data centers. So they're constantly cooling all year long. When it's 10 degrees outside, they are pumping heat off their roof as they're cooling off all those computers. And we're pretty much capturing that heat. And we're putting it into our piping in the wintertime. It's going to go across the 16th Street and go into this campus here. These are 3 of 11 of a larger campus of New York City Housing Authority buildings. Currently, they're on Con Ed District Steam for both their domestic hot water and their heating. So what we're going to be doing here is we're going to be converting all 3 of these buildings to domestic hot water to U10, capturing the waste heat from the data center. And then we're also going to be testing one of the buildings I'll get into where we're going to be doing heating and cooling in that building. And really the beauty of this is in the summertime, when they're using the air conditioning, that heat is going to go right to these 3 buildings using domestic hot water. So we're actually being able to kind of recycle it. And then if there's any excess heat, all these cooling towers up here in this building, there's a lot of excess capacity to do cooling. We're going to send it right back to them, and then they're going to cool it for us. So it's really try to streamline this project a lot. What it looks like, though, this is one of the big challenges. So this is a retrofit project. So this building you see up here, it has steam radiators. Directly steam comes from Con Ed, goes in, steam radiators. How do you manage to get this converted to U10? It's only 2 ways you can do it. You can run all the pipes and everything on the inside and tear everything up, or you can run on the outside. We're trying running on the outside. It's hard to get into buildings, especially nicer residence buildings, and we want to limit the construction in their buildings, not to offset the residents. So we're going to be putting in similar like you see on the split unit, right? We're going to be running our refrigerator line. This is actually not refrigerator, VRF system. We're actually running water lines up and down to each of these areas, and we're putting in air handlers, condensers with the fan coils in each of the units. So each unit will have about 3 put into their apartments. The other part we had this problem in this project is space. Manhattan's very tough for space. So on the other project, you saw a nice big building we built. We really can't do that. So what we're doing is we're optimizing the basement space. So in the bottom half of this building is actually an unused basement, which is very rare in New York. So we're able to go into this basement and put in most of our energy center equipment, the heat pumps and everything, and really take up every square inch of this basement to be able to kind of utilize that for our equipment. Same thing is true on the energy center, the thermal resource building. So at 85 10th Avenue, that data center building, we're actually, instead of building that building, we found an unoccupied old storage space for their restaurant, and we're putting all the equipment into the space, the pumps, the heat exchangers and everything, so we can eliminate the whole need for an additional building for the energy center. So it really saves a lot of time and really taking advantage of what we can do. All right, last project here is in somewhat of a landmark place here, Rockefeller Center. So Rockefeller Center, down where the Christmas tree is and the ice skating rink that everybody sees on TV. It's actually a great campus. Most of these buildings, about 11, 12 buildings here, are all owned by Tishman Speyer. And they do an amazing job right now of doing exactly this, waste heat. They have ice chillers, so they make ice certain times of the day, and they burn ice at other times. They use the waste heat to transfer the buildings. They do an amazing job. They're still very much cooling dominant, even in the winter. You look upside, you're right by NBC studios, and you just see the hot air coming out in the wintertime. So we're capturing that, and we're putting it into a pipe. This is a heating-only system, and we're going to take these three buildings here, 1221, 1230 Avenue Americas, and 605th Avenue, and we're going to be converting their heating from steam over to the U10 network. A tremendous amount of loading here. I mean, you're talking about like 2,000-ton heat pumps being put in here to provide that heating. Really exciting project. Again, if you look at it from down at the street level, you get to see the magnitude of these buildings. They're very large buildings, large commercial office buildings. Best part, none of the tenants will even know we're doing it. The challenge was getting across the street, though. So to get the piping across the street into this area here was extremely challenging. We were fortunate enough to find a little space for the Energy Center building, same as last time, in the loading dock, very close to where they bring in the SNL skits for the loading dock area. We got to get some space there where we're going to build our Energy Center in this really tight area to put all our pumps in there and the heat exchange that we need. And that's really key for us to find a space to be able to pump this. The other problem is getting across the street. And we did a test pit digging across 6th Avenue, and this is what it looks like. There's not 1 inch there. We tried our best to get our pipe to snake in. We knew it would be tight. I mean, most of our careers have been digging up Manhattan streets, but it really was no space. We had this extra thick concrete there, so we had to be innovative, and we are. So why it's so tight there is because this line here depicts the subway station. And that subway station is only 7 feet from the top of the road. So we decided to go through it. So we're working with the MTA. We're actually designing a system that's going to go across the wall and go across the top floor of the subway station. And we're going to run our whole UDS system. We're going to manifold it and go right across the street there. It's really a great opportunity because we have a chance now to find a way to connect New York City buildings that have all this load and it's dense, but you can't get the pipes across. If you think in a more innovative way, we can do that. And this is really, really excited about this project. All right. I didn't go over my time. I didn't get to stop, so I'm going to turn it over and save for questions. Thank you.
Oh, God. Hello, everybody. My name is Aaron Miller. I'm with SHARC Energy. We are a Canadian company. We are in the wastewater energy transfer business. And you'll hear about waste energy heat recovery, but we're actually energy transfer because we're talking about heat source, heat sink, just like geothermal in a lot of ways. So what I'm going to do is highlight a few projects that are currently in design, different phases of design. Sorry to be so New York City centric, but this, as Greg said, Con Ed has really been gung-ho. We've got a bunch of UTENGA projects in development around the state, but I wanted to show you, it's moving forward on its own. Wonderful. I wanted to show you 3 projects in particular that are in design. Amalgamated Housing Corporation, Whitney Young Manor, which we discussed earlier, and Alafia, which actually Salis O'Brien got awarded last night for the top jobs for mixed use. So we're very excited about that. Amalgamated Towers. So this is low-income housing in the Bronx, and we are looking for a way to capture the sanitary water before it leaves the building. I'm really loving this. Sanitary water before it leaves the building, to use that water to make potable hot water for said building. The rule of thumb is if we can capture 100% of the wastewater before it leaves the building, we can provide 91% of the domestic hot water load for that building. It's almost a one-to-one circular economy. It's quite brilliant. And this is what's really cool about this, and you can read this faster than I can read it to you, especially because I'm under the clock here. This is going to be a phased approach, and this is one that's very important. These projects can be really big, as Greg was describing, and massive undertakings. You don't need to bite it all off in one time. You can take it off little by little, what makes sense. Progressive, to me, means pragmatic. You have to do what makes sense. It has to pencil. So here, we've got 2 of the towers of a multi-tower campus that we're focusing on as phase 1. So we're going to capture the wastewater before it leaves the buildings, and we're going to put piranha in the building. That's shark, piranha, you catch on. So, and the piranha literally uses the wastewater, solids and all. If you can flush it down a toilet, you can pass it through the piranha, and we're making potable hot water. And as you can see here, and I should probably put on my old person glasses so I can read, we're able to grab we're able to provide, 72% of the domestic hot water for these buildings. And phase 2, we're going to do 2 more towers, and eventually the plan is to add pods of geothermal that will then allow us to connect to the Piranha as well with a secondary heat exchanger to take that 72% up to 100%. And then ultimately the entire campus will be connected with an ambient loop. So now all the buildings will be sharing the energy between the loops and the sanitary load. So again, it's a really exciting project. And one of the great things about this, as you can see, in addition to making all this potable hot water, we can clear up the roof space. We don't need cooling towers anymore. So now you can add solar PV, or you can put roof space up for, for the residents to enjoy it. So again, it's expanding the functionality of the buildings in addition to offsetting the energy required to keep them running. Whitney Young Manor, which you mentioned earlier, is currently in construction. So I should mention, Amalgamated, we're still in design right now. We're trying to figure out the best way to try to connect those buildings. My apologies. Whitney Young Manor is actually in construction right now. This, as opposed to the Piranha, we have our SHARC system, which is our larger heat exchanger. Essentially, it's a very specialized wastewater heat exchanger and a very specialized filter on the front end that removes enough of the large solids out that we can run the wastewater through that heat exchanger to do our thermal transfer without the heat exchanger getting jammed up. So right now, the SHARC is in the basement, the baby SHARC, and they're currently, this is wild, it's all about thermal storage. We need a battery because in multifamily res, we have diurnal peaks, morning showers, and in the evening, you've got showers, you boil pasta, bathe the kids, do dishes. So we're trying to capture as much, if not all, of those peak flows so that during the low peak periods, especially overnight when electricity is cheaper, we can make the hot water or do the heating and cooling, whatever we need, and at a much more efficient and cost-effective methodology. So right now, because the sanitary pipe that essentially connects these 2 buildings to the city is about 4 feet under the foundation, we're excavating out the foundation to create a tank so that the wastewater will enter on one side of the tank and leave on the other side, one high, the inlet slightly higher than the outlet, so we have gravity overflow through the tank, so boiling solids pass right through, heavy solids will fall at the bottom, we'll pull those out with a sludge pump, and then we're left with this nice tank full of rich wastewater that we can now run through the SHARC, through our heat exchanger to feed the process loop, and then there'll be water-based heat pumps connected to that process loop to do the heating, to do the cooling, and the domestic hot water production. And as you can see here, in addition to the energy savings, there's also massive carbon offsets. And in New York City, where we have Local Law 97, we're going to deliver some real savings here to avoid carbon penalties that are going to kick in very soon. Come on. Now it doesn't want to go forward. And this last project that is now in operation, and we're actually going to be taking Con Edison and some people from Rockland, Orange County, and some other folks on a tour on Tuesday. This is a multi-phase project. This rendering is the full campus. Where's that little, is this the middle one is the light? So phase 1 is these buildings over here, and there's 2 large towers connected to a common lobby, which is Alafia C1, C2, and then across the parking lot is C3, a smaller building. And we have 2 Piranha HCs in the basement of Alafia C3 producing 100% of the domestic hot water load for said building using a combination of the sanitary and the geothermal. So in the wintertime, when that geo loop is pretty cold because they're taking all the heat out of the loop to heat the apartments, we're using the 72 degree some odd Fahrenheit wastewater from the toilet, showers, and sinks in the building to make 140 degree potable hot water for the building. And in the summertime, when that loop gets heated up to about 90, 95 degrees because everyone is now pushing heat from the heat pumps into that loop, the Piranha is programmed to switch over to the loop to pull energy out of the loop to make the potable hot water. So between those 2 systems, we're able to, produce 100% of the domestic hot water load for C3. C1, C2 is a different animal. It's a much bigger project, whereas C3 has 35 boreholes. Originally, C1, C2, when Salas did their analysis for the geothermal, they were going to need 125 boreholes to pick up the entire thermal load of the building. And this was mind-blowing for us as well. They were like, hey, let's drop SHARC in. We'll grab some of the heat out of the waste stream, make potable hot water, heat the building. But it turns out that the real value was heat sink. Passive house design buildings are very cooling dominant. So by putting the SHARC into the system and using it to pick up just the peak loads, this is wild, just the peak loads of those few really hot days in the summer, they're able to right-size the bore field from about 125 boreholes down to 93. So there's a massive first cost savings for the project. And now moving forward, by pushing and pulling energy in and out of that sanitary stream, we're able to keep that bore field dialed into that perfect temperature around 68 to 82, depending what you need, to keep the heat pumps operating at their maximum capacity and efficiency. So a really, really fantastic project. We're moving people, they're already moving people in. Residents are using both buildings, and it's a really exciting project. So I welcome the opportunity to have my friends at Highmark or Con Ed, or myself, or a combination thereof, to take you down, to show you the project. And what's wild, again, because it's a phased project, phase 1B, phase 2 are already in design. They're going to mirror these buildings and do them again, do them again, and do them again. And each set's going to have their own pod of geo wells. And then again, at the end of the project, the plan is to connect the entire campus with an ambient loop. So again, all the buildings at that point will be sharing, pushing and pulling energy in and out of the loop as needed. So again, a phased approach, generally speaking, for these large projects is the right way to go about things. And I wanted to end on this one. I guess that's 3. I'm blind. Sorry. 1. Oh shoot. All right. UBS Arena. We did a study for this one. We went here originally to go look at a geothermal project out in the parking lot, but turns out too much of a pain in the butt. But they have a ejector pit that collects all the wastewater from the club level. Turns out that we figured if we just take the wastewater from that pit and run it through a piranha, we can make 91% of the domestic hot water, or the 100, it's not really domestic hot water because they're using that water to resurface the ice machines. Turns out that they have very, very large Trane chillers in there to keep the humidity and the temperature in this building perfect so the ice stays nice and smooth. Well, on dark days when there's nobody in the building, you can actually hear the chillers because they're ramped down so low. So now we're going to take some of that extra hydronic heat off the Trane chiller plant, run it through the Piranha HC, take that hot water production up to 100%, and thereby also, as you can see, provide an additional 288 MMBTU of cooling for the building. So it's a win-win all around. So again, if you've got wasted hydronic heat in any form, call us. We're your Huckleberry, because here's an asset that we didn't think we could use, and we're finding now a way to repurpose it for a very useful cause. And if only anybody knew, a hockey guy in the geothermal space, we might be able to add this around to the rest of the NHL. So thank you for your time today. Really appreciate it. This is exciting.
How's everybody doing today? Chris Devins with Trane. Been with Trane about 15 years. My decarb journey started in an Irish pub in Syracuse about 7 year ago. Engineer drew out a napkin how he was going to heat the city of Syracuse using what in his words was the most efficient, reliable compressor he knew of, which was a Trane centrifugal. I didn't know what the hell he was talking about, but I was all in. Learned a lot since then, and what he was talking about was a chiller is a heater, right? That we just need to focus on what's coming out of the back end. I'm going to talk quickly about some alternative approaches to decarbonizing our buildings. You've been hit pretty heavily over the past 2 days on standard approaches to geothermal, so we're going to hit some more niche opportunities. Right off the bat, water pumps don't make water. Everybody knows that. If I told you differently, you'd think I was an idiot. Heat pumps don't make heat either. They use energy to bring low temperature heat to a higher temperature. That lift is described as the difference between the leaving water temperature out of the condenser to the leaving water temperature out of the evaporator. In a lot of these examples, we're talking about boosting that heat up. In some examples, cascading that. We need heat sources, whether it's wastewater, geothermal, heat recovery. The cheapest BTU is the BTU we already have in the building. We need to really focus on that as opposed to having to extract it out of the ambient air. We can do it, but it's inefficient and it's expensive to do, to install and operate. So what we're really talking about is, if we're talking about existing chiller plant, how do we capture the heat off of that? Maybe an existing chiller can get 95, maybe 110 out of that. Well, if we put that leaving water temperature out of from the condenser into the evaporator of another chiller heater, a booster, whatever you want to call it, we can then drive that up another standard set of lift to get our usable hot water temperature. So booster options, hot water generators, chiller heaters, heat pumps, whatever you want to call it, we're very fortunate at Trane to be able to have, such a broad portfolio to where we can really look at what the lift requirements are, the leaving hot water temperature requirements, capacity, as well as efficiency, reliability, and simplicity of the system. If all I had was our modular heat pump line, I would look at every job like, how can I shove as many modular heat pumps in there? If all you have is a hammer, everything looks like a nail. We're very fortunate to be able to look at an application, come up with the best approach for that job. We're going to talk about heat recovery cascades. This is not for every job. It's not meant to be for every job. A great example for this might be large district plant steam to hot water conversions, campus level conversions for that. You've got 20 buildings that need 180-degree water. We can do that with a single compressor, but is that really the right way to go? If we hook that up to a geothermal loop as our heat source, do a standard set of lift, maybe 45 in, 35 out, back to the well field, get about 110, put that into the evaporator of another chiller heater, which is the same Trane centrifugal we've been making for years. It's not new technology for our techs. We can drive a COP at worst at about 150 degrees of lift and about 3.5 on heating only, not even considering the simultaneous. So another unique application might be dual temp systems, right? Hey, maybe we want a decentralized cascade. Let's put 120 out to all the buildings that can handle it. But we've got 3 or 4 buildings that there's nothing we can do. It's a massive cost overhaul. Let's put a booster in the basement of that. Let's then boost that up to our 180-degree water, right? Maybe we don't need the whole plant to be 180. Maybe it's just in an individual building. Let's boost the certain areas that need that 180 and let everything else run at 120. Another application that we've been working with a lot of healthcare facilities right now and trying to tap into the Empire Building Challenge, heat recovery ponds. What can we do with hospitals and existing facilities that have a high temp hot water load and a significant cooling demand in the winter, right? Why don't we, we're going to go into this example right now. Sorry. So existing example of a hospital. Let's say it's a 1,000-ton plant, 200-ton load in the winter, steam boilers, right? As is today, we are adding heat into that system for our heating load with the steam boilers, and we're using our chiller and tower to reject that heat at the same time of the ambient air. We can't use that as a heat recovery chiller because it's only getting 120. We need 180 there. So why not, instead of ripping this whole system out, add on to this system with a booster? When our heating is greater than our cooling load, rather than running our tower, we're going to keep those BTUs in the building. Extract that out of our building, put it through our standard chiller, put that into our booster to get 180-degree water. We're then going to handle the rest of the load with our hot water boiler. That's not going away. We need that natural gas infrastructure. Healthcare facilities have a 80% reduction goal by 2050. We don't start taking measures now, we're not going to be able to get there in 24 and just flip a switch. We got to start taking the opportunities we have. So how would that work when the cooling load is greater than the heating load? Well, our boiler is going to be off. We're going to reject as much heat as needed for the heating load to that booster, and any remaining heat is going to go out through the tower. One thing that facilities are really liking the prospects of is in the summer, if we don't need a heating load, that's just a chiller. That booster is just a chiller. So we're adding redundancy and resiliency to their cooling plant when they don't need hot water because we can run that in a standard cooling configuration. And maybe they have a low temp load. Hey, let's get 120 out of that. Deliver that to our handle all the reheats, and then reject the rest of that heat out of the ambient air. I might put it on the wrong slides, but hey, so that was examples of coincidental heat recovery, meaning the heating and cooling load is happening at the same time. If we aren't storing that somewhere else, we don't have the ability. All you have is what your need is at that moment. That's where thermal storage comes into play. Obviously, geothermal is a fantastic opportunity of that. Can't do it on every job. This is a typical building load profile. Let's say a nice office building, a lot of people, a lot of glass. 48-hour load profile shown here. Building comes on in the morning warmer-up. That's going to be our peak heating load typically. Then as that day goes on, people and solar load increases, cooling load is going to increase. Now, most of the time we're handling it with air side economizer. We crank that down, then we're going to be able to keep those BTUs in the building. But if we don't have any place to store those, we better be doing air side economizer, otherwise we're running a chiller for nothing. So what if we actually use that heat, stored that heat, to heat our building the next day? Geothermal is a great example of this, but what about thermal storage, thermal batteries? If we use this in the form of a thermal battery, we can store that heat for use the next day. So we're talking about ice storage here. We've done ice storage for cooling only applications for 50 years. Ice was the original form of refrigeration. In an ice storage cooling only system, our battery is charged in the morning when our tanks are full of ice. We are then going to, typical application, you're going to have 60% of you're going to size your chillers for about 60% of your peak load. 40% of your load is going to be handled by that ice storage. Throughout the day, you are going to reject heat out of the building through your tanks, melting that ice, and the remainder through your chiller tower or air-cooled chiller. At night, you need to recharge that battery by making ice again so we can use it the next day. It's utility rate arbitrage. We are shifting demand off our peak to lower our peak demand usage and our demand charges and lower our utility costs. So what if we tried to reverse this cycle? If we were trying to use this for heating, our thermal battery would be charged when it was full of water. So in that morning warm-up, we are going to extract heat out of the water to heat our building. When you extract heat out of your water, what are you doing? You're making ice, right? We like to play with the phase change property of ice because it's a very dense form of energy. So we don't need massive tanks. We're talking about smaller tanks and footprints, obviously an issue everywhere. As that load increases, the cooling load drops throughout the day, we're going to reject that heat out of our building because we've already cranked down our air side economizer. We're going to use that to recharge that battery. We are going to cool our building with the ice in the tanks while also providing heat out of our chiller heater, heat pump. On the coldest days, we're going to need additional heat source, right? It's not going to be enough. If we end the day with tanks full of ice, we've got to be able to melt those for the next day. So whether it's a wastewater system, an air-to-water heat pump, or using natural gas infrastructure, we need to recharge that battery by melting that ice again so that we can extract the heat out again for the next day. That's it. That was fast.
All right. I welcome anybody to ask questions of any of the panelists.
Sure. Hendricks with Willdan Energy Solutions. A question for Greg. Greg, you got a lot of pipe there. How much heat do you lose moving through the pipe, and do you have to recharge that once you get to your sink?
Yes. So, I mean, really, depending on the project. So, in the Manhattan projects, we're really only seeing about a 2-degree loss across the heat exchanger you're getting from where we extract. So, for instance, on our Rockefeller Center project, we're coming out at 92 degrees. Across the heat exchanger, we're coming down to 90. So we're not having a large loss. It's insulated pipe. In the Mount Vernon project, it's an ambient system, right? So it's almost it's not as relevant because it fluctuates in temperature, and we have dispersed different bore fields and different thermal resources spread across our network. Or right now we're down to 4 decently large bore fields. So it's not a really great impact to the projects.
This question is also for Greg. Brian Posner from NOCO Energy. For the building where you're bringing the pipes up on the outside, are you guys leaning towards leaving the steam infrastructure or ripping it out?
Yeah, that's a good question. So right now we have this one main steam service that feeds all 11 buildings of that facility. So the main steam service going into the building, we're keeping. But on top of that, we're also using that steam service, and we're having a new dedicated small service just for Con Ed that we're going to have a heat exchanger, a shell tube heat exchanger. That's our backup heat for the whole system. So the way it would happen is that, if in the event that, for whatever reason, again, we're utility, it's probably not needed. If you're doing it on the private side, you probably wouldn't have this level of redundancy. But we want to ensure that we can, so we're actually going to be able to inject heat into our loop to make sure they have the heating there. So it's staying in place, and the radiators are going to stay in place just so we don't have to disturb them in the residents' apartments.
Thank you.
Hello, Elizabeth McCorvey, Family Resource. This question is for Lauren. You said on this heat recovery, we did apply, and but you said, is there a cap per unit? Because I understand it has to be less than 5 for you.
Hi, Elizabeth. Thank you for your question. Yeah, so it's available to multifamily buildings. NYSERDA's definition of multifamily is 5 units or more. So on a per project basis, the cap is $40,000 for the assessment, $80,000 for the design, and the project can be kind of determined by the project team if that's one building, one multifamily building, or multiple, if it makes sense to do multiple.
The last question is, with your $2 million for phase 3, can we combine buildings together? As you said, two families, that single families are not eligible. So how does this work? Can we combine, or does it just have to be multis?
Yeah, the eligibility is still the same. Multifamily buildings, if there's multiple multifamily buildings on a campus or, connected together under the same ownership, then those can be applied under that $2 million cap. But yeah, it's still the same eligibility of multifamily.
Yeah, Rami Gergis from MA Engineering. The question is for Chris. You mentioned that the hospital need to reduce the energy usage by 80% by 2050. Is this a federal or a state, or where this comes from?
Anybody else said that? Just thought. I thought it was a part of the Climate Change Protection Act.
Okay.
But I guess I'm not positive. I bet there's a lot of people in this audience who have that answer, though. I apologize.
There was a goal that was defined in the CLCPA regarding 85% reduction of greenhouse gas emissions by 2050. That was what was laid out in the act that was passed in 2019. But it's not requiring hospitals or campuses to achieve that type of goal on that timeline. It's a target on a statewide basis.
This is for Chris. So we have a bunch of your chillers, about 60 ton, I think, 60 ton in modules. Can we reverse them, that rather than use the condenser water for say domestic hot water?
So there has to be a reversing valve. That would be a true heat pump. A non-reversible heat pump is any chiller you've got. So we just need to be focused on what's coming out of the condenser, right? So yes, I would say that you could use your chillers to get the heat off of that and turn those into heaters. We're more focused on then controlling to the leaving water temperature and the flow through that condenser loop. Can you get it for your necessary lift and hot water? I don't know exactly. I'm not sure what specific chillers you have, but happy to talk afterwards.
All right, thank you.
And that was Tony Gelber from Pratt.
Hi, Josh Einbinder from NY Green Tech. This question is for Greg. On the Chelsea project, you mentioned the challenges of working in the infrastructure of Manhattan. For the connector from 85 10th Avenue Data Center over to the residential buildings across 16th Street, were you able to use existing infrastructure or piping, or did you need to put in a new pipe across that 16th Street?
Yeah, no, in that case, we're gonna be putting in. Keeping in mind, we're at the tail end of design, so we haven't started construction yet. But we're putting in new pipes. We're putting in 2 new 10-inch pipes that are gonna be connecting. And it's tricky. Like some points, we have to dip pretty deep. We have to go about 17 feet deep in some areas to go under some sewers. So New York City's congested. It's not an easy run or a long run, but it is 2 10-inch steel pipes to go across.
Emma Legel, Pace Energy and Climate Center. Also a question for you, Greg, on the other New York City project. Hadn't heard about the kind of use of the subways for running the lines before, so I think that's like a really interesting kind of thing to know that's happening. Are you able to give a little more detail on like how MTA kind of gave that approval, and is it something that's being looked at as like potentially being able to do more of, to actually find a way to run lines without having to tear up roads?
Yeah, I mean, so we always knew that was an option. So we look at that project designing. We wanted to try the street side and the MTA side. It's still tight even in the stations. But really what came about, well, one, we were kind of running out of options, right? Because the street side looked pretty bad, and to relocate a lot of those facilities would be tough. On the MTA side, really, it's a revenue stream for them, right? They charge us to have anything in there right away. So with congestion pricing always up and down, it's pretty attractive to be able to have potentially some revenue coming in from having our facilities there. So it's not necessarily a cost-effective option, but more than potentially a way to actually, you know, make those connections.
Spencer Baracco, Lori Engineers. My question is about the SHARC systems. There have been some concerns in the past with maintenance requirements for something that has a lot of sewage going through it, and what other things people may be flushing down the toilet. So could you speak to that a little bit and your experience with that so far?
Sure thing. It's a great question. Again, the Piranha is designed, it's got 4-inch and 6-inch inlets and outlets. So if you can flush it down a toilet, you can pass it through our system. So I don't want to say we don't care. There was an assisted living facility in Australia where we had to put a mass array on the front end because they were flushing the craziest things down the toilet you wouldn't believe. So for the most part, we're okay on that front. And the Piranha really only needs like biannual, possibly even just once a year cleaning to pop off the top, check out the seals and hose down, make sure the HMI, there's almost no moving parts, very easy to maintain. The SHARC has more moving parts. You have a macerator, you've got a filter, low pump, the heat exchanger. So we recommend quarterly cleaning. And again, in this case, Highmark Service Department, union guys trained up on how to do this stuff. We recommend for the first ones, like two technicians for about 6 to 8 hours. Right now, we have a project in Vancouver. We have 5 880s basically providing enough hot water for 23 million square feet, dealing with massive amounts of sewage. My guys can get all 5 of those machines cleaned in about 6 hours now. So if you design the wastewater holding tank, the battery, if you will, and the pumps inside that tank properly, maintenance of the system is really, really simple. You get those tanks and pumps wrong, and not so much. But it's a great question, and but we've been doing this now for 15 years, and knock wood, it's been or whatever this is, it's been successful. Thank you.
I think that's all we have time for.
Right. Thank you so much. Thank you to the panelists.